Okay. So hello. So today we finish this topic about ordinary differential equations with a non-Lipschitz singularity. And we address the other two cases, so the other types of attractors, which is first it will be periodic and then chaotic. So let's just recall our setting. So our ODE is have this form dx dt. The right hand side is R alpha f of y. So it's a vector of d dimensions. R is a distance. R and y are spherical coordinates essentially. So R is the distance and y is the unit vector along x. So it's in a sphere, and alpha is smaller than 1 for having non-Lipschitz condition, for not having Lipschitz continuity at the origin. Okay, and then this function f, so we have 0, we have a unitary circle, so we have that y point here, and the vector f, capital F, can be expanded into radial part of Ry and the tangential part of S. So f of y is fr of y by y. So this is real plus tangential part, which is in, so this is in tangent plane to the sphere at point y. Okay. So what we did is that we could associate a rescaled system to this equation. And this rescaled system, it lives on a sphere. So it's a regular system which is for vector y, but in different time. So it's time which we call S, and it's defined only by a spherical part of the field. So we will call this equation star. So this is this lives on a sphere. And then we can reconstruct original variables implicitly. So the variable z, which is log of the distance. So it's solved as z0 plus integral from 0 to s of r y s prime ds prime. And then the time is defined, the relation between time t and s is state dependent, so it depends on the distance. So it's we rescale time with a factor which is a power of the distance, which gives you the equation for the time. So the original time is exponent of this. So it's 1 minus alpha z s prime ds prime. So you just put r as exponent of z and integrate, right? So this is what we get. And we had the central construction which has to do with the way how we understand time. So the original time had a blow-up point. So this, let's put it in the middle. Okay. TB. So there was a blow-up, and this blow-up it's a finite time singularity, which means that the solution which starts at certain initial condition enters to the origin, okay, in finite time. So whenever it enters to the origin, in the rescaled time, S goes to infinity. So it's a kind of a rescaled system. It spends the whole life. So this is S, so plus infinity. And then if you consider the solution which exits from a singularity, it also a solution of the same system, rescaled system, but now it starts at minus infinity. And it's written in terms of different S. So it's, let's say, S tilde. So there are kind of two different lives of the system. One before, while the first system it just has a solution which passes for singularity, in the rescaled coordinates there are two different solutions which has infinite life. So it's first until infinite future, and the second after the blow up from an infinite past. So this S tilde corresponds to T. And the problem was that the transition is non-unique because there are infinitely many solutions that you can put after. So what was done is that we were putting the regularization, which means that a certain interval. So remember, so what we did. So there were solutions which were entering singularity and then exiting, right? And then there were infinitely many of them. So what we did is that we regularized system in certain neighborhood of the singularity of radius nu. So we changed the vector field so that whenever it enters, it exits uniquely. And in terms of time, there are two times. One time corresponds to entrance to the regularization region, another to the exit. And this time, it gives us entrance time S and exit time S tilde. And what regularization essentially does, it connects the point here to point there, right? So it connects the entering point to the exiting point, which defines essentially which solution is chosen, okay? So this is regularization. And all of this collapses to 0. So in the limit, nu goes to 0. So whenever limit goes to 0, this interval collapses. Even though it collapses, it still has infinite large pieces in both sides. But whenever it collapses, this region collapses to the point. It means that we may select something special. So the behavior is such that so limit as nu goes to 0 of S, the entrance time is plus infinity, and limit as nu goes to 0 of exit time is minus infinity. Good. So that leads to two conclusions. So first conclusion was that then you can characterize pre-blow-up and post-blow-up. So the solution before TB and after TB. So what we had for pre-blow-up, which means T smaller than TB, it means that since S goes to plus infinity, which means that whenever you come closer to the blow-up, your behavior will be determined by the attractor. So the solution is controlled asymptotically by a focusing attractor. Focusing means that it's a attractor which corresponds to FR negative. So it's solution which approach 0, attractor. Just because time goes to infinity, so whenever time goes to infinity, if you're in the basin of some attractor, you will approach this attractor asymptotically, and this will define what happens very close to TB before. And quite different situation is the post-blow. For the post-blow-up, which means T bigger than TB. So for post-blow-up, the limit is opposite. It's not that we send the regularization time to infinity, plus infinity, we send it to minus infinity. So we send it to our far past, which means that whenever we reach any finite time, the time interval is getting larger and larger in the implicit limit. So at any finite time, we're exactly the attractor. So it's not asymptotic, we should be exactly the attractor. So it means that solution belongs exactly to not asymptotically. So one it was asymptotically, and here we're exactly to so in this case it's defocusing. No? It should be attractor which expels the solution. Defocusing, which is FR positive attractor. And then we have this example for this for the case of fixed point. So example with fixed point attractors was, I just recall what was the example. The example was a special field which had a form. So all solutions, so all x's were like this, and all solutions which were starting on the left was entering the singularity, and on the right hand side they were either exiting or passing through. So all solutions on the upper part they start from singularity. And so this was the original system. Then we had a rescaled system on a circle. Right, so this is a circle, and there were two attractors. On the left, FR was -1, so it's defocusing. No, it's focusing. Here FR was 1, so it's defocusing. So it means that the left attractor is defines blow-up, pre-blow-up, and this is post-blow-up. And the solutions were approaching these two attractors. So there's which, and from this you can make a conclusion, say that whatever typical regularization you define in this neighborhood, and you can make actually the precise statement. I'm not going to give it because it's technical. So whatever regularization you put here and then collapse, what you obtain as a solution. So these will be solutions start with x1 at 0 negative. So let's consider solutions with initial conditions here. So whenever you have an initial condition there, you know that you first blow up either along the loop or along this curve below. Then you enter the singularity at 0 in finite time. So it means that asymptotically, your blow up is always approaching this solution along the horizontal line, which corresponds to the focusing attractor. But when you exit, you should exit exactly through the defocusing attractor, which means that you don't have any freedom anymore. So at post-blow-up time, you exit along this straight line. So this gives us unique solution, globally unique solution. So that situation that we'll see, it's similar to the Burger's equation, that we have infinitely many solutions after blow up, but whenever you impose regularization, and send vanishing regularization, you choose a unique solution after blow up, and it does not depend. So in this case, this choice does not depend on how you regularize, practically. Okay, so here I'll take. So this is for those who want to have a note on the course, A, B, C, D. So there are some. So I already gave a project 1, if you remember, about pre-blow up for the shell model. So project 2 will be consider some field Fry in 2 dimensions, similar to what I did. So I gave this field for our example with this sine cosine. So you just take another one, just make something, create something nice, and study attractors of a rescaled system. And conclude about pre and post blow up solutions. So what is the pre-blow up solution? What is the, depending on initial condition, what is the asymptotic pre-blow up solution, and what will be post-blow up solution if you make a choice with the regularization? So this is a project that you can do analytically, so it can support numerically. So that's a second thing to do, and then send it to me. Okay. Good. So this is what we had before. So now we move to the next question: is what happens when the attractor is not a fixed point? So which are the next option is the next simplest option is a periodic orbit. So periodic orbit. So let's assume that what we have in the post-blow-up dynamics is not fixed point. So this is not fixed point in higher dimensions. So this should be at least d should be bigger or equal than 3, right? Because on a circle we can have periodic orbit, but that will be trivial example. So in order to have something not trivial, we need d to be at least 3. And it means that the post-blow-up dynamics is defined by the periodic solution of this system on a sphere. So we have some solution which is, let's call it y equal y periodic. And periodic means that there is a period. So y periodic at s plus t, period t, is the same as y at s. So there is some period. So what it means that we have now like dimension 3, for example, then we have a sphere. And then there is some periodic orbit on the sphere of this equation. So whatever solution you choose in some neighborhood, it will approach this asymptotically, this periodic solution. So what will be post-blow-up dynamics? So what will be dynamics here? So we can make actually complete computation in the example. So let's consider example in the sense that we simplify the situation. Let's take Fr to be constant, which is positive on the periodic orbit. So let's consider that Fr is a positive constant on this point. In this case, we can just make all computations explicitly. So we can find how z depends and how t depends on s. So let's just make this computation. So z is what? So it's so Fi is constant. So integral is just s, Frs. So it can be written as Fr s, and then I put constant here. It doesn't. So instead of z0, I put s0, just to make it simpler. And then, so it's fz of s. And then we can, so that means that r of s is exponent of z of s, which is exponent there. Good. And next time, so for the time we consider this first relation. Is r 1 minus alpha ds. And then we use this exponent. So it will be exponent 1 minus alpha of r s minus s0 ds. So now we have to integrate. So now remember that how we integrated in the post-blow-up dynamics. In post-blow-up dynamics, TB corresponds to minus infinity. So this gives us the integration constant. So we need, so T goes to TB when S goes to minus infinity. So it means that we can integrate this relation from, so on the left we integrate from TB to T. And here we integrate from minus infinity to S, right? So that's same integrations for both sides. So then on the left-hand side, you will get T minus TB. And on the right-hand side, when you integrate this business from minus infinity to S, you just put this coefficient in front. And this coefficient is positive. So exponent at minus infinity will become 0, which means that you can just write exponent minus alpha. So that's an equation. Or so T of S is TB plus this expression. But now you remember that this is R, and it enters here. So it enters as R in the power 1 minus alpha. So what you have is T equal TB plus R one minus alpha divided by this whole stuff. R 1 minus alpha divided by I5R. And then you can express R. So you have to put this here. It will be R of T is 1 minus alpha R T minus TB 1. So we have a solution, how distance depends on time. And this is a solution which exits, so at t equal to b, it is in the origin. So we have a solution of distance, but now we also need the other part. So we also need the angle. In order that if you want to have angle, how you do it? So this is so we have one piece of formation. So the second piece is the angular part. Y of S is periodic solution at S, but now S we can express it. We need to express S in terms of time. So how we do it? So first we express S in terms of Z. From here. So remember, so Z of S is what if R, S means 0. So you can express S. So S will be 0 plus Z over Fr. And Z is logarithm of R. So it's 0 plus Fr. So, good. Good. So now finally we find that Y is Y periodic, and then we put S from this. And R we know how it depends on time. which means that we found the solution. So this is the second piece. This is the second piece. So the final solution will be that x of t is r of t by y of t. And this is end. So essentially, we found the solutions which in this case can appear after the blow up, and they depend. So these solutions. So this is solutions parameterized by parameter, because here we have a 0 which is arbitrary. And a 0 enters into the periodic function, so it parameterized by 0 modulo t. So what this means? It means that our consideration of the exactly this consideration that solution belongs to the attractor after the singularity. So the singularity is here. So it's at least three-dimensional. It tells us that in principle, if you have initial condition, some initial condition, and then you enter the singularity, so you have a blow up, then whenever you exit, the theory tells you that there are not just a single way of exiting. So so you exit somehow, but there is a whole family of different solutions. That can exit. And these solutions depend on this parameter S0 modulo t. So that somehow looks to be bad, but in fact this is, I will show that this really appears in real models. So what you can prove in a general setting, so I will not give a proof because it's long technical derivation. So if you want to see, it's our paper of nonlinearity, journal nonlinearity, 2021 by Theo Derivas and myself. So what you can prove in general that all periodic solutions are obtained in the subsequence limit. So now, again, the limit that we obtain does not depend on regularization. But in principle, it's not unique. So the subsequent limit is that nu n is taken as exponent minus fr tn plus s0. And you see that n is real, or is integer, so it goes to 0 as n goes to infinity, and n is integer. So you can choose special sequence of viscosities of sizes of the ball the way you regularize. independently on the regularization. You a priori know how which one you choose, and this is a geometric progression, which goes to 0. Here it's mean value. So this is fr. It's in general when fr is not a constant, so it's a mean value. And whenever you make a limit, you choose different solutions which depend on S0. So you get different solutions that you have here. So you have really, you can obtain any of these solutions in the limit for the periodic. So the case of periodic orbit is already is showing that non-uniqueness can be true. So it can be truly physical non-uniqueness, which will remain even if you put regularization. But at the same time, depending on, you still can have subsequences which converge, and they converge to just one parameter family of the solutions at the post blow up. And finally, the most important case, not most important, the most counterintuitive case is when we have a chaotic attractor. So what happens when the attractor is chaotic? It means that the dynamics between the regularized moment and any moment where fixed moment when you observe. So in this interval, which is becoming infinite in the inviscid limit, the dynamics here is chaotic. So this dynamics is chaotic. And this means that whenever you have any error brought in the regularization, so you have to put small error. So any error that you put in the regularization will be amplified to the finite error here. So whatever you observe at fixed time will be random variable. So you see, if you assume some error or some noise inside this small neighborhood. So if you say that, okay, we regularize, but we don't regularize exactly. We regularize with there is some perturbations, there is some error. And error is usually physically always exists at small scales. So there is some uncertainty how we regularize. So this uncertainty, whatever it is, it will be amplified by the chaotic dynamics to the probability distribution, which is just probability distribution of the chaotic attractor. So the probability, so you will get a probabilistic value at this point with a probability which actually does not depend on this error, because it only depends on the attractor. So essentially, so what we have graphically is this can also can be proved in some special situations. So it was done in our next paper. So essentially, what you have in a chaotic attractor is that given initial condition, you have a blow-up solution, so it enters in finite time to the singularity. And then when it exits, it actually exits it infinitely many different ways, depending on what is the noise realization inside. And whenever you fix time, so you consider some time, so this is at t equal tb. So whenever you consider some fixed time t bigger than tb, your solutions are described by, are random. So described by a certain measure, probability measure. So probability measure on, okay. So it's given by attractor. So attractor defines a probability measure with which you will choose the solution. So you see, you have many interesting properties. So what is the interest? So we can just list them. So what we have is that whatever regularization you put, so it's important that you have to put a regularization with some noise. Whatever regularization you put, the choice of the solution is now random. And random and non-uniqueness are two very different concepts, because non-uniqueness means that there are many solutions. And random means that there is a probability. So there is a probability associated to the choice of every solution. So there is a probability measure given by attractor. So again, given by attractor means that it's independent of regularization. That defines which trajectory you choose. And finally, we can just mark that it's about importance of noise. So importance of noise. So you cannot obtain the implicit limit unless you put a noise in the regularization. So of noise for implicit limit. So essentially the result is that, the result is somewhat counterintuitive. So we have a deterministic, so let's better say formally deterministic initial value problem for ODE with this non-Lipschitz singularity. So the differential equations is deterministic. So initial condition deterministic, but it has which has a unique stochastic solution. So the choice is non-unique, but stochastic solution in the sense of measure, probability measure. Is unique. So what you gain is that you lose uniqueness of the specific solutions, but you still keep the uniqueness in some sense. So what is unique is the probability distribution. And this probability distribution does not depend on how you regularize. So again, the system somehow, even before being regularized, already knows what will happen. So this is all, no. This is essentially all theoretical part. So what I said here, it has some proofs, rigorous proofs in some special situations. But much of the thing, especially extensions to other models, are all open problems. So there's few known. So after the break, I will show you specific example of different systems where we can mostly numerically demonstrate all these situations. So periodic orbits, fixed point, and chaotic behavior. So essentially, we can demonstrate all these kind of behaviors. So break, no break. Ok, vamos começar então. Pode ser, né? Já começou? So hello. So let's see some examples. So first, this is just let me put it bigger. So first, this is this example that we considered. So this was a vector field in 2 dimensions. So the second project that I like you to do is just to substitute this vector field by something different. So you just put different quadratic expression here and try to see what is a vector field. And this is a rescaled system on a circle, so which shows 2 attractors. And the right attractor corresponds to the post-blow-up dynamics. So whatever solution enters, it exits through this green line. So there is this global uniqueness. Then in 3 dimensions, we can arrange another situation. So we can arrange periodic attractors. So this is an example shown in these small letters. But anyway, this is explicit vector field of the form that we considered. And it has a property that there is a period. So this is a rescaled system. So a rescaled system lives on a sphere. So it's 3-dimensional sphere, and there is this periodic orbit which is shown in black. So you see, whenever orbit you have, it approaches this periodic solution. So it means that so these are two different views. So red corresponds to the expelling, and to the defocusing part, blue is the focusing. So there is this defocusing periodic limit, and what it means that whenever you take this subsequence limit along the geometric progression, so this geometric progression of viscosity goes to 0. Whenever you make this limit, you will converge to the solutions that enter singularity and exit along the certain specific solution. But this subsequence depends on the parameter xi. And if you choose different xi, you get different solutions. So you actually can exit in parametric family of different solutions after the singularity, depending on what is very small nu. So it chooses. It's actually still very small subset of all non-unique solutions, because there are much more non-unique solutions, but we choose one parameter family of this solution depending on viscosity. And then finally, this situation is when the attractor is chaotic. And in that case, we need to make regularization to be random. So it means that this regularized field is maybe something deterministic plus some noise. So it means that whenever you pass through a regularization region, you exit in different places depending on some random component. So but whenever you take a limit, of viscosity going to 0, this region, which depends on the physics, for example, of your model, collapses to a point, and it means that you impose some probabilities for the solutions which exit. And as we saw, that this probability distribution does not depend how you regularize. It is defined by the attractor. So I think it's also nice to have an example for this situation. So where it is. And I can give you. So this we have this example in the paper. So we need an attractor on a sphere. So the chaotic attractor requires at least dimension 3, which means that sphere should have dimension 3. So the original space dimension 4. So this was a specially designed system in dimension 4 of this form that we consider. It made such that it has a chaotic attractor, and you will recognize that the chaotic attractor was made out of Lorentz system. And then we give initial condition. So this, what I will show you the movie. So this is a time minus TB. So there is a blow-up time. At certain time before the blow-up, we put an initial condition. So I cannot plot 4 dimensions. So I will plot just x1, x2, but there is x3, x4. So remember that I'm just plotting 2 of them. Actually, I had to put 2 projections. I didn't think about it. So I put just x1, x2. And then this green point is in our initial condition. So what you will see that it will, in finite time, enter to the the origin and then exit. And so what will whenever it enters to the regularization region, so we consider regularization region very small, so 10 minus 5, so you don't see it. So it's tiny, and it's given by certain regularization, which is random. So there is kind of random, very small random perturbation that solution gets here, and then we exit. So what we will do is we simulate how this solution evolves. So just let us see, and then I comment how it is. So this solution, the solution is unique because the field is smooth, except for that point. So at that point, it's non-Lipschitz. It enters, so it becomes slower and slower, but since it's non-Lipschitz, so we will enter infinite time. We know that we enter infinite time. When we enter, wait, time gets 0. So see proof is entered. So it received a very small perturbation, and now I will show you. So let's see, and then I comment what is shown. So actually what is shown is, let me see how many. 1, 2, 3, 4, 5, I think 6 or 7 different solutions. So every time you kick, every time you make a simulation, you kick, you get something different after the blow up. So the green points show some 6 or 7 different realizations. And this brown yellow area is a result of, I think, like 100,000 of simulations. So it shows the probability distribution. So it's density. So the density shows that darker region means that more solutions are found in this place and less solutions in this. So it's a probability distribution at that time obtained through this 100,000 simulations. And the green points are just specific simulations that I want to show. So you see very clearly that after the blow up, it shows a stochastic behavior. So we do not select one solution, we select many of them. But what is important is we select them with a unique probability distribution. So uniqueness is inherited by probability, not by the solutions themselves. So this is how many? 1, 2, 3, 7. So there are 7 specific solutions and 100,000 solutions shown by this color. So somehow what we can say that whatever regularization we put, very small regularization, we know that we have no chance to predict what will happen after blow up, because every time every realization will give absolutely different solutions. You see, green points are in very different places, but we have a probability. We know that with certain probability, for each region, we know the probability with which we can find it. By the way, this is exactly the probability that you see in weather prediction, because weather prediction, as we will see examples later, is supposedly spontaneously stochastic. So whenever you have it's written that it's 25% probability that there will be rain, it's really this probability. So it doesn't mean that in 25% of area it will rain. It means that maybe it rains, maybe it doesn't. So So this region, for example, corresponds to rainy behavior, and this is no rainy behavior. And we know that the solution will be obtained there with just 25% probability. And there is no way to improve this result. So it's really probabilistic. Because this probability is rooted in some noise which you do not control. So it's rooted in the noise in a very, very small neighborhood. So let's just see it again. So you see that. So you start with certain initial condition. Before you meet the singularity, you are unique. And after you meet the singularity, you are stochastic. And surprisingly, this is a solution, stochastic solution, which solves deterministic equations with deterministic initial condition. So you see this. So just four ordinary differential equations that you can write and solve, so you see how complex can be the behavior. Okay, so these are ODE examples. So we can also have more complicated models. So first of all, we can first example that I can mention is behavior of particle. So you see, if you have some velocity field which is given, so assume that you know velocity field which depends on position and time. And now I want to compute trajectory. So I want to look at a certain particle, and the particle trajectory satisfies this simple equation. So the velocity derivative of the particle position is equal to velocity. So we have ODE. So now this ordinary differential equation, if the velocity is turbulent, we know that the developed turbulence corresponds to the velocity, which is, so if you remember this lectures by Simon, so the velocity field is non-Lipschitz. And unlike the example we considered, it's not non-Lipschitz just in one point, it's non-Lipschitz everywhere. So somehow this is an example where we have a non-Lipschitz, non-uniqueness everywhere. So this is a field which is everywhere non-Lipschitz. So it's continuous but non-differentiable. So it means that in principle you can have this phenomenon of spontaneous stochasticity at all the points. And then there are results. So there is this review. So there are rather recent results, a couple, more or less 20 years ago, which are rigorous, and they considered velocity field which is non-Lipschitz and defined by certain Gaussian stochastic process. So you can really produce this velocity field and prove that whenever you put a regularization and then take a regularization limit to 0, so this usually the regularization is used, for example, use Brownian motion, so it's a different form of regularization. So then the solution remains stochastic. So what that means that if you look at certain particle, which is at certain specific position, that at larger times its position is already undefined. So it goes in many different ways, and all you can uniquely predict is a probability distribution. So at larger times it can be anywhere with certain probability. So probability is unique, realization is not. So next question, we can go back to the Burgers, and Burgers equation, so we know how it evolves. So whenever you take this Burgers equation, so f here is u squared over 2, and then there is viscous parameter, viscosity goes to 0, and we already considered this example. So we know that typical solution is that, so imagine, so this is the initial condition, so it's just zoom of some sine function. then it becomes steeper, 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 and then the red point corresponds to the blow up. So it develops infinite derivative. And after that, it develops shock. So discontinuity, which is this blue line. And in fact, you can make all these rescaling procedures. So there is a blow up time, and you consider before and after, the dynamic before and after, and you introduce this rescale time for the logarithm. So it's s minus log, it's before, so it goes to infinity when you t approach tb, and then plus log, it starts with minus infinity. And if you can make this rescaling procedure. I don't want to give you details, but anyway, you can see that pre-blow up correspond to one attractor. So this is a attractor which corresponds to the dynamics at plus infinity, and post-blow up correspond to another attractor. So there are two attractors which control pre-blow up and post-blow up in Burke's equation, which is essentially similar to the situation we had with the ODE. We had one blow up for one attractor for pre-blow up, another attractor for post-blow up, and they controlled. The first controlled how the blow up, the symptomatic form of the blow up, and the another controlled of how the what happens after. So essentially, with the Burgers, we have two attractors in a similar situation. The next is shell model. Remember, we considered shell model, and shell model had a blow-up behavior. So this is a plot. So you start with certain initial condition, and you have a blow-up in finite time. So what happens after? So now there are two shell models. There are actually two shell models that you can consider out of the same shell model. So remember the shell model, where it is. Yeah, shell model has this form. So you can cook two models out of this equation. One model is when all of u are purely imaginary. So if all of them purely imaginary, they remain purely imaginary. So this is the first model, which is called Gledzer. So this is a behavior for, it's not UN, it's modulus, absolute value of UN. So what happens? You give initial condition. So it's U1, U2, U3, U4, and so on. So there are infinitely many of them. They blow up at finite time. And then if you put very, very small viscosity, you can continue. And each one continues normally. You see that there is a small, but in a kind of funny way. So there is each solution continues. And if you take different viscosity, also very small, so you will have exactly the same behavior before, but very different behavior after. So what you can actually see is that if you don't just take another small viscosity, but viscosities which go to 0 as power of 1/16, so power of -4 multiplied by integer number. In this case, it converges. So you take another viscosity with larger n, so it will be much smaller viscosity, but you will see exactly the same picture. So it will converge. But this sequence, it depends on a parameter, or this psi, which is between 0 and 1. So different parameters will give different limits. So essentially, this you can see. So this is a behavior, and I will just plot U3 and U4. So these two, red and blue, as function of time. So depending on which limit you take, you are unique until the blow-up point, and have very different solutions after blow-up, which form this tube. So after blow-up, you can have different solutions, and in fact, you can have a special representation. What you can do is, remember that we associated blow-up with a traveling wave. So you actually can associate post-blow-up with periodic traveling wave. So you can make a special representation of the solution and already directly see the periodic blow up or periodic wave. So you can see this periodicity in the post blow up dynamics. So in fact this situation is very similar to this periodic attractor for the post blow up dynamics. And finally, we can consider this shell model in its original form. So everything is complex. And when everything is complex, so what we have, so when everything is complex, what we have? So we have this situation. So this is simulations. These numerical simulations, which are obtained with a very small noise and very small viscosity. So put very small viscosity. Actually, viscosity here. What is the viscosity here? So viscosity is 10 minus 15. So it's incredibly small viscosity. And then we put a very, very small noise, like 1% of perturbation at very small scale. So it's U36, you make a small kick. So the result is like this. So you see this is U8 as a function of time. So before the blow up, it's unique. After blow up, so we have 3 different realizations. And if you make 100,000 of them, you can see that they form a certain probability distribution. So this color shows what is the probability to see different values at a given time. And this is for U8, so all of them like this. So this is U13, so all of them. So the solution is deterministic until blow up and stochastic after the blow up. And this stochasticity, this probability distribution does not depend on very small viscosity and on the way how you put noise. So this is something completely universal, but depending on initial condition. So this is what I told. So this is unique dynamics before blow up, unique probability distribution after blow up, but this probability distribution depends on the choice out of infinitely many non-unique realizations. And it does not depend on regularization. So this is something already specific for the system. And just like with ODE, we can associate it with a chaotic attractor. Actually, here we can associate it with a chaotic wave, and we can just directly visualize this wave numerically. So this wave is, so you see what I show you? I show the probability distributions for different ratios of the solution depending on the time tau. So tau is S, is now S is tau. So you can see that in S, in variables and S, we have a traveling wave solution, chaotic traveling wave solution. It's chaotic because it's a traveling wave in terms of the probability measure. So that are artificial examples, but still already closer to the reality. And now I can show you the simulation of already physical model. So this will be related to the spontaneous stochasticity. So actually, so all of these phenomena that we discussed are we call them spontaneous stochasticity, because what it means that well, it is stochasticity because the solution is stochastic, and spontaneous is because this solution solves formally deterministic problem. So the equation is deterministic, initial condition is deterministic. So the stochasticity appears spontaneously because of the presence of the singularity. So
Is it always impossible to do we always need to add noise toward renormalization when the post blow up attractor is chaotic?
Yeah. Yeah, because normally it's related to the theory of dynamical system. If you, so in order to have a convergence to the, so it's a property of convergence to equilibrium. So so if you start with a random initial condition given by a certain measure, and it doesn't depend what measure is, but it should have some nice properties. So it should be, for example, absolutely continuous. So there should be some distribution. Then at large times it will converge to the measure of the attractor. So you need some, you need to introduce some stochasticity into the regularization. So somehow you put a stochasticity into regularization, but then you remove it because you collapse the region where you introduce this stochasticity to a point. So you put, so somehow you introduce stochasticity to formulation artificially, then remove it by reducing this, by collapsing this region to a point. And though you removed the, in the limiting process, you removed the noise, or you remove the stochasticity from a formulation, but stochasticity stayed in the solution. So solution remembered. So it's somehow you introduce some property and remove, but solution already does not forget it. And it does not forget it in a special way. It keeps stochasticity, but it will not depend on the way how you introduced this noise into the regularization. So somehow noise is just a procedure how to select a solution. But this selection is very rigid. So it does not depend, it's not sensitive to how you make it. So somehow solution, already original system knew how it will, what will be a probabilistic distribution. It knew it, and this way of regulation with noise is just a way, the way how to recover this information. So some rather interesting fact. So okay, so we will talk about spontaneous stochasticity in Kelvin-Helmholtz instability. And Kelvin-Helmholtz instability is what? Is instability of the interface between the two flows. So imagine that there is a fluid, and the fluid in the lower half plane moves to the left with a constant speed, and the upper half plane it moves to the right. So just two fluids just moving. If the interface is straight line, it's a solution, because just the upper fluid does not interact with the lower. And even if you put viscosity, okay, they will interact, but they will still have a solution where upper part moves to the right, lower part moves to the left. But whenever you put some perturbation here, this situation changes tremendously. And situation is, this is because whatever small perturbation you put, it's unstable. So it will develop in large-scale structures. And smaller the viscosity, more complex the structures will be. And you can see it. So this is I think this should be in some atmosphere of some planet. I don't remember which one. So you see that there should be two flows, which one goes to the maybe to the left and other to the right, and they form this instability here. This is atmosphere. This is in the Earth, so it's always it happens all the time. Just you don't see it. And here, because there are clouds, you see how that happens. And this is a picture of Van Gogh. So Van Gogh, you can see it. It recognizes that there is a Kelvin-Helmholtz instability. So it's often on his picture. So okay, so we just simulate it. So we take. So it's called vortex sheet because upper part is a constant speed, lower part is a constant speed, so the vorticity here and here are zero, but vorticity is a delta function in between. So That's why it's called usually vortex sheet, or it's a discontinuity. So it's a line where the velocity jumps from positive to a negative value. And then you cannot simulate this picture without viscosity, because this is an ill-posed problem for partial differential equations, but you can simulate it if you put viscous forces. So if you take Navier-Stokes. And Navier-Stokes simulation is like this. So what we do? We put viscosity, and we put very, very small perturbation as a noise here in the interface. So in the beginning, it's just, so what we plot is vorticity. So red is a vorticity. So in the beginning, vorticity is just concentrated in this small line. So this is initial condition, you see? So it's initial behavior. It just becomes thicker because of viscosity. So nothing happens. But then it starts to create, it's unstable. Because of small perturbations, it's unstable. It starts to create small vortex blobs. So they roll around each other, normally merge or split. So they form bigger ones. So the merge and split, they form bigger ones, they form bigger ones, and so on. So this is behavior. It never repeats itself. So every time you put different noise on this line, you get absolutely different picture at given positive time. So now, so this is a clear situation where you put regularization, you take a limit, there is no limit. And you can do it in different ways. So our first way was to put viscosity. Another way is, if you had fluid dynamics, you probably had the, a topic of point vortex approximation. So you can represent the dynamics approximately with point vortices. So it's just a point which has a certain vorticity, and whenever you take many points, you can approximate essentially any velocity field. And the good part is that point vortex approximation is actually ordinary differential equation you can solve. So this is a point vortex approximation of the vortex sheet. So here's something like 100,000 points. And we just simulate this. So, and you see the very similar behavior. So they kind of form some structures, they form larger structures, they form larger structures, and so on. So it's at small scale, it's different. So at small scale, it's different. But from larger view, it looks the same. And this can be quantified. So essentially, I'll only show this picture. So this picture shows a 2 points correlation. So it's a function how we measure the relative values. So the values of vorticity at two distant points. And what you can see is whenever you, I don't know what happens here. Oh, interesting. So whenever you decrease viscosity, at small scales, you have something different, but as you decrease viscosity, it all converges to the same line. This is observable. And also, if you increase the number of points in the point vortex approximation, you also converge to the same line. So essentially, it tells you that in the limit of vanishing regularization, so in the limit when the viscosity goes to 0, or in the limit when the number of point vortices goes to infinity, so essentially the limit where you approach the behavior of the ideal fluid, in both limits you converge to the same distribution. So this is just quantitative evidence that there is a convergence first to the probabilistic behavior, and the second that it is the same for different regularizations. So it means that this behavior is probably spontaneous stochastic. Certainly there is no theory whatsoever which so far approaches theoretically this behavior, but numerically we see that most likely has spontaneous stochastic behavior in the Kelvin-Helmholtz instability. And it's resembling the behavior in ordinary differential equations with a point singularity. So just to have a small, I'll just give a small conclusion. So what we saw that what can be proved for ordinary differential equation and what can be verified for the more complex system, including the real fluid dynamics, is that we apparently see the spontaneous stochastic behavior. So spontaneous stochasticity. So this is phenomena which was essentially, you can track it back to the works of Lorentz, but it still largely fails any rigorous theory, though you can see it rather well numerically. So what components it has? So first, already what has to do with the word spontaneous, it has to do with a formally deterministic system. And it's usually it must be non-Lipschitz. Because if it's Lipschitz, it cannot be stochastic. Lip system. So system is formally deterministic. So the equations are deterministic, the initial condition deterministic. Then the non-Lipschitz mean that it has a non-unique solutions. So non-unique solutions does not a priori mean that it's spontaneously stochastic, because we saw that in some examples you choose just one of them. So what this system must do is that it realizes a random choice of solutions. So it's non-unique and random and deterministic. And at the end, it gives a unique, so the uniqueness only remains in this probability, in unique probability distribution. So now we can just also comment on what is the difference between spontaneous stochasticity and chaos. Because somehow it resembles chaos, but it's not. So let's say chaos versus spontaneous stochasticity. So what is in chaos? So deterministic chaos has to do with so remember, with exponential amplification of the error. So exponential amplification of error. It means that if you give an error to the initial condition, at initial time, it will generate a much larger error at larger times, which can be estimated as initial error multiplied by exponent lambda t, where lambda is the largest exponent, so the lambda positive is the largest let's say Lyapunov exponent. Usually largest Lyapunov exponent. So you see that initial error is amplified exponentially, which means that increasing time, exponent is usually a very fast function. So even if you put very small error initially, it will become very large at larger times. But if you take the limit of initial error to 0, then also the error at any fixed time also goes to 0 at any fixed time. So it means that it's really deterministic. So it's if you have an error, it will increase. But if the error, but you can, but still you can exact prediction by reducing error enough. So what we have in spontaneous stochasticity is the difference. So the error, so here in spontaneous stochasticity, the error is amplified independently of initial error. And actually the reason is exactly in a non-Lipschitz condition. So you can qualitatively you can see what happens if you substitute this relation, which is exponential, by the relation which is power law. So consider the behavior which is initial error plus something which is power law, constant T alpha, where alpha is bigger than 0. So consider this kind of amplification of error, which is one of the possible strategies for the spontaneous stochasticity. So you see, at time equals 0, you recover your initial error, but as delta x goes to 0, so removing the initial error, it doesn't matter. So error is still positive. So unlike in the chaos, if you remove initial error, you remove error at any time. And in spontaneous stochasticity, doesn't matter how you remove initial error, you still have error growing. So this growth of error is due to the non-Lipschitz property. So there is this internal mechanism that produces the stochasticity independently on what you gave it, on how exact it was initially. So that's it. That's it. So then I think tomorrow I still give you so the next two lectures will be still related to spontaneous stochasticity. Tomorrow I will give you the system which is not an ODE, which is infinitely dimensional and which we can resolve by hand, and where we can see it in full, the spontaneous stochasticity. So here I told you that in ordinary differential equation, if we have an attractor, then we have a spontaneous stochasticity, but I never showed you example. And actually, putting an example and proving anything here is rather complex. So, but tomorrow I show you example with infinite dimensional system, which really, in some sense, qualitatively resembles equations of fluid dynamics. And we compute everything, and we just directly see non-uniqueness and see that how spontaneous stochasticity evolves. And just see, and we will see how strong it is. So how strong it is So how fast it evolves in somehow nearly realistic situation. And then on Friday, we will see more. So the Cyril will give a lecture on the methods of convex integration. So this is a branch of mathematics which developed in recent decades, which somehow showed that situation with Euler equations, non-incompressible Euler equations, is somewhat similar. So at least it has a very strong non-uniqueness property. So at least in the real fluid dynamics, this second point is really non-unique. So we have very strong non-uniqueness, which can be shown rigorously. So it somehow supports this idea of spontaneous stochasticity already on a rigorous ground. So then see you tomorrow. Thank you.